Might be watching this from home. This is our last unit on waves for physical science physics. So on the front page, we see wave terminology, wave properties, and then ultimately we're going to look at waves and technology. So I want to talk really briefly about why we do this last unit. The state of Michigan redid the state expectations for physics about 5 years ago. This is how this course got generated. Was we said every kid has to have at least one semester of physics. There were some key things that we wanted kids to be able to do. Understand basic forces and interactions. So they said on the state expectations, were like, kids should build a device that tries to minimize force on impact, right? And so that's what your drop project was about, understanding the force and time connection. They said conservation of energy is critically important to the way the world works. Kids should be able to build a device that transforms energy from one form to another. That's what the projectile launcher thing was about. Another one, they said electricity and magnetism, super important to the way the world works. Kids should understand evidence that electricity can be created from magnetism and vice versa. So your speaker project came out from that. The last one has to do with waves. And they said today's day and age, almost everything is communicated digitally via wave-related phenomena. So we said we got to cover some digital communication stuff. Now, back when I was your age, my professor at the time, this was in college, he's like, a great way of understanding analog versus digital. Raise your hand if you understand the difference between analog and digital kinds of things. Only a few. Okay, not many hands being raised there. Analog is sort of like, if you want to get to the top of the stairs, analog would be like a ramp, continuous signals. You can have any value, any height along that ramp you could be at. So analog signals like that, that's an analog clock. You can have any placement of those arms or those hands that are going around the clock. Whereas digital is more like a staircase, where there are discrete steps, if you will, that you can't have any values in between those step points. So it's only digital values or discrete values. Most of our communication is done stepwise, not analog. So there's a bunch of communication protocols that take advantage of digital communication. So we want to make sure you understand that as a end of year kind of goal. Okay, you guys have your wave project identified. Again, you're just going to be looking for the history of the device, how it works. The last week or so of content that I'm going to be covering with you is to try to give you some wave-related phenomena. Some of it's review, some of it's new. So I'll try to do a lot of demonstrations on things that are likely new. A lot of the things that are review, we just sort of hit on those and make sure you understand them. All right, so we got your projects. Okay, what properties of waves? So again, you guys understand the drill, right? We have a guided note packet. For people that are watching this at home, the note packet that you have go along with this, and then hopefully this will help you. Wave is simply a motion of a periodic disturbance. So when I say something is a wave, I'm going to disturb this slinky, and this is the first time I've had a chance to really work with the slinky. So I'm going to create a disturbance along the slinky. And I notice that disturbance propagates over there towards CJ. Now, CJ, you're tall enough, you can probably reach up and grab hold of that, right? So how long does it take for that disturbance to propagate between me and CJ? So I send him a disturbance, and it takes a little bit of time. And can you feel it sort of go through your hand? Yeah. Okay, send me one back. Okay, so again, I don't notice anything until it gets to that point, and then I can feel that. So the disturbance propagates through what are called internal forces. Thank you, CJ. So internal forces, our first unit of this course was to talk about how forces can cause changes in motion. And so Newton's laws come into play. Internal forces within the medium allow what's propagating. CJ, when I sent this to you, what would you say it was actually propagating to you? I wasn't sending you matter, right? I wasn't sending you like a golf ball. What was propagating from me to you? Say it again. A wave, and we would say that was really just the wave is transmitting energy, right? So really what's being propagated is the energy of that disturbance. So energy is flowing through the medium. Now, the disturbance, you notice the disturbance traveled between me and CJ in a straight line, whereas the particles will oscillate. Now, we haven't really studied oscillating motion before. And so, well, when you guys built your speaker, you guys noticed that the speaker was oscillating up and down. Probably too quickly for you to be able to see it, but you could certainly hear it. I think did I do the demonstration in the beginning where I just had the speaker being driven by 1 or 2 cycles per second? Could you guys see that sort of bouncing up and down? But then as I increase that frequency, you can start to hear that as sound. So we have something oscillating. The kind of motion that medium goes through is what's called simple harmonic. Now, I have an asterisk by that, and I want to emphasize, especially for those that are not here today, there's a lot of asterisks in this set of slides. Those asterisks mean that the content is not going to be on a quiz or an exam. That is mostly there because it could be a part of your project. So depending on what you chose for your project, you might have to talk about simple harmonic motion. So there will be a lot of things in these lectures that are there for enrichment, if you will, that are project-based, not exam-based. Waves require no bulk transfer of matter, so energy is transferred very efficiently. So you remember efficiency was a big part of our launcher. How efficient is that energy transformation? Waves are characterized by very efficient energy transformations. We can send things incredibly large distances with very minimal energy needs. Okay, so again, the idea behind this, CJ, you're a golfer, and I'm sure when you hit a golf ball, you expend a tremendous amount of energy to be able to get that ball to travel from the tee box to, how far you drive it? What'd you drive? Say it again. 250. All right. A lot of energy involved here, right? Now, this is not the right kind of thing. I don't have my golf clubs with me. But you do a tremendous amount of work going through and putting a lot of energy into that club motion to be able to get that ball to travel about 250, 260 yards. The amount of energy it takes for me to send something like this, and again, the idea behind this is that, would you agree that this is very little amount of energy, but I'm able to transmit it a great distance. And that's basically because the energy is being transmitted as waves. So they're very efficient is what I'm trying to get at. Okay? So energy transformation is mechanically very inefficient, but this one much more efficient. I'm going to have you guys, I want you to take a look at this site. I'm going to show you the previews of it. This guy used to be a professor for Kettering University. Before it was Kettering, it was called GMI. You heard of GMI before? Okay, General Motors Institute. So this is big in the automotive industry, right? So General Motors, the big three and stuff like that. So he worked for them, and now he's been a professor of acoustics and vibration at Penn State for many years. And so I love his website, and he's got a tremendous number of visuals and simulations for people to look at. So first one I wanted to look at is just what is a wave. Now, as I zoom in so you can see this better, you probably have looked at waves in this way, where someone sends a disturbance across like an auditorium, watching a football game or a basketball game, something like that. The disturbance is propagating from left to right. So that's like a person wave. And if I could show it, I would have you guys do this here. So Vinny is going to start the wave. And Jonathan, you guys start the wave? Okay, there you go. It's going really slow. I know, these guys are supposed to go. Good, and then one more, now it reflects back. You notice what happens here, CJ, when that hits the end, you might notice that it comes back, correct? Can you see it come back? So you guys got to send it back now. Go, Jay. Go. Way back. Okay, you guys march back. You guys need to drink some coffee or something like that. All right. So nice job. Now we're going to go this way. Good. All right. Oh, now it's supposed to come back. All right. Good. Now I want you to close your eyes. Close your eyes. You guys look like you're so Connor, Wayne Company. You guys are going to start way in the back. You guys are going to start. You ready? Go. Yeah, you guys don't know. So without your eyesight, you don't know which way that force is supposed to propagate. So the idea behind that is that you need to have some internal forces. Now, down here, you notice that the red bar on the left is the source of the disturbance. And so you can see the source of the disturbance is on the left. It's propagating through that medium. And you notice what's moving there is not the particles. The particles just sort of oscillate. So they go from the left to the right. The energy flows from the left to the right, but there's nothing that's actually moving other than the energy. Now, if I were to do this continuously, so now what I have is some source of disturbance on the left that's creating a wave. Yeah, I notice the red dots are particles that are vibrating, but they're not moving anywhere. They're simply oscillating back and forth. And so we would say the wave is moving linearly, or from the left to the right, but the particles are oscillating. Okay, so there's a piece of tape right above Reagan. See the piece of tape roughly around there? Can you see it? Yeah. Okay. I normally have an alligator clip up there, but if I take a look at this, as I send this waveform through this, you'll notice that all that piece of tinfoil does is it oscillates through its equilibrium position. So the energy is able to flow through it, whereas that just oscillates. So I'm not moving energy from left to right, or I'm not moving particles from left to right. I'm moving that energy. So again, that's the key feature of waveforms. Now, what I'd like you to do is I'd like you to take a couple of minutes and research through this site. There's probably about 40 or 50 different things that you could look at. What I'm going to ask you to do is find one that sort of strikes a chord with you, pun intended, and make a comment on this posting about what you found interesting. So if you go to your classroom page, so if you've heard of that concept called what struck a chord, I would ask that you take that, do some look through there, and just post for me a comment on the classroom page of what you found interesting, some simulation. Okay, so take like 5 minutes, research, find something that you find interesting, make a comment to this thing here. Will you please post the link though? So whatever it is that you find interesting, take a link of that. So you post that with the link and then add a comment. What was it showing me? What did you find interesting? 5 minutes, please. Okay, so if you're watching this from home, the link that I sent out there, so what struck a chord with you, I would encourage you to look through this. There's more animations and things here than I would have time to be able to show in class, but you might find something interesting that sort of strikes a chord with you. So again, it has to do with waves and then applications of waves. Okay, if you haven't started to make a comment in there posting, could you take a moment and please put that down, what you find interesting? Maybe take a link, a copy of that link, put it on there in case someone wants to look at that down the road. They can have your 2 cents on it. So take a few seconds to create a link for me. What did you find interesting? Okay. Okay. Okay, so Shay, thank you. Struck a piano chord. You could see the waves sort of moving along the string. Appreciate that. Connor, shift in frequency, wavelength, the wave of a moving object. Good. Prove the universe is expanding using sound waves. I had not seen that one. Hey, you found something on there related to that? Cool. So is it using sound or was it using light for that? Could you tell? Really? Okay. Interesting. Good. There's so many things on here. I would not be able to get through all of them myself. Coda, motion of air within a guitar. So it's not just the strings that vibrate, the actual air part of the acoustic guitar. You can see the air vibrating as well. Jonathan, non-dispersive medium with the constant shape. Cameron, CJ, sorry. Article talked about different frequencies. Yeah, for a hockey stick, when you hit it, sometimes that stick will vibrate erratically in your hands. Same thing with a golf club. It has to do with vibration of modes. We'll look at that as well as part of this. And then Riley, temperature increases with height. Oftentimes you'll see sound across the lake. You'll hear sound being able to sort of curve downward. You can hear sound going across the lake really well due to something called temperature inversion. Doppler effect, pretty cool. Temperature decreases with height also, and then some other things. And then Chase, or Wyatt, you had something on here, then it went away. String of the guitar going back and forth, good. So someone in my 4th hour, and this has to do with the next topic that I want to look at. So something 4th hour that came up. And again, there's more things than you could find than you could have enough time to be able to look at. But this is one from Kiera. It said, the speed of a wave depends on the elastic and inertia properties of the medium through which it travels. And that really was a good segue into this next thing that I want to show you. And so how quickly, like I mentioned, CJ said, how long does it take for that wave to get from you to I? A lot of it has to do with the properties of the medium. And so Kiera's comment there really led nicely into this next thing. So I want to take a moment and start looking at this now. You notice that on this slide, this is an asterisk for a lot of this. So it means that it would not be on your exam or quizzes. But this has to do with something called simple harmonic motion. Due to restoring force directly proportional to the negative displacement from equilibrium. Now, if I recall, Equilibrium was a first unit. First unit concept. If you take a moment and refresh your memory by sitting next to that person that you're sitting next to, tell them what we mean by equilibrium. Will you take a moment? What's that mean when I say something's in a state of equilibrium? And you would say when the forces add to what? Zero. Yeah, Rango hero. Yeah, when forces add to zero. So an object is in a state of equilibrium when the total force acting on it is zero. We could describe that with an equation. And again, you're not going to have to use this equation. It's called Hooke's law. But you would not see this on an exam or an equation or on a quiz. So Hooke was a contemporary of Newton. And so one of the things that Hooke is known for is development of this law, that the restoring force is in direct proportion to the displacement from equilibrium. That negative means it's restoring, it's trying to bring it back. Now to demonstrate this, I'm going to use this thing here. Now we have not studied this kind of motion as of yet. If you look closely here, you'll see a cart that's held in its equilibrium position by two springs. So these springs on either side of this are maintaining it in a state of equilibrium. Now, everything that's made up of matter is held together by forces that keep it in a state of equilibrium. When I displace this from left to right, it's the restoring forces that try to bring it back to equilibrium that keeps that thing centered. So I'm going to take this thing off to this side. I pull it over about 20 centimeters. And then when I let it go, what I notice is that it oscillates back and forth through its equilibrium position. And it would do that indefinitely if it wasn't for friction and that sound that you can hear coming off of that. So this is what we would call a simple harmonic oscillator. Raise your hand if you play a stringed instrument. What do you play, Coda? Is the guitar ever out of tune and you have to tune it? What do you do to change the tune of a guitar? You have to adjust the tension, right? Yeah. Okay. Now I have another setup here that has much stronger springs. Now, the springs holding this one in shape are much stronger. So it's sort of like if the cord is a little bit loose or if it's not as tight as it needs to be, you can adjust that tension. What does that do to the frequency at which it vibrates? What's it do to the tune that you're playing? Does it increase or decrease the pitch? Yeah. So if I increase the tension force and I let this go now, you notice that oscillates much more quickly. So it's the same basic idea. It's held together by stronger restoring forces. So when I displace it, it has a tendency to oscillate about that equilibrium position. So you have some things that oscillate rather slowly, and then you have other things that oscillate much more quickly. It has to do with two things: how much mass I have there, and how strong are those springs holding it in place. So your guitar has different weight strings, right? So if you have more mass, it tends to resist changes in motion, so it vibrates more slowly. But if you increase the tension, I can get that to vibrate more quickly. A little bit of physics involved with those oscillations. Okay. Now what I'm going to ask you to do, this is a review of stuff for your final exam. So this is a set of pie charts to show energy at the various locations for that mass on the spring. What I'd ask you to do is use these two values, PE, and that could be elastic, and kinetic energy, which is energy of motion. You take a moment and tell me what belongs in each one of these pie charts based on where that thing is in its motion. So you notice it's at its far end point, it's at the middle, it's at the far end point, and it's somewhere halfway in between. You take a moment and tell me what belongs in each one of those things there. Take a moment. Just try it. If you're watching this from home, you might try that yourself. We're going to look at the answer here in just a moment. Okay, the form of energy you'd expect way at the end point. When we release this thing, way over here, far to the left, the form of energy that we have there is called PE, it's potential energy. So we would say at the end point, it's PE. That'd be elastic potential energy. Of course, at the other position, at the far end point, when it's way at the far right, that would also be PE. So whether or not we stretch or compress that spring, we have energy stored in that position. Now, as it goes through the equilibrium position, I notice it's moving really fast. So it's got a really large velocity. That's where its kinetic energy is greatest, and so we would say its kinetic energy is maximum at the middle. And then anywhere that I look, doesn't matter if it's at the end point, the middle, or halfway in between, the amount of kinetic energy and the amount of potential energy would always add to what's called the total mechanical energy. And I don't know if you guys remember that. TME, when you guys did your bar graphs for your mechanical launcher, you guys had 100 units of energy that you put in. Then we saw some of that got transformed into total mechanical energy. Here I have a pendulum. And that pendulum is another one of our oscillators. I'm going to let you guys try to draw for me a graph of what you think the energy looks like at the various locations as this thing sort of swings back and forth through its equilibrium position. So here I have a pendulum, swings back and forth. This one has far less damping on it, and so this one will last quite a bit longer than these things over here. What I'd ask you to do is to try to construct for me a graph of energy as a function of position. So as it swings all the way from the maximum left, all the way to the maximum right, and then all the way down the bottom, what would that energy look like at those various locations? Try that. See if you can do that one. TME stands for total mechanical energy. We're saying that that's a constant, so that dashed line along there says that that value is the same no matter where I look. Agree or disagree? Gravitational potential energy. Gravitational potential energy is a maximum, agree or disagree? Gravitational potential energy is maximum in the middle. Agree or disagree? Good. Gravitational potential energy is actually maximum at the endpoint, so I'm going to go ahead and draw the gravitational potential energy. Looks like this. So the red represents GPE. It's maximum at the ends, and it's 0 at the middle. That would be the wave. That would be the graph, if you will, for gravitational potential energy as it swings to and fro. Now, when it loses gravitational, what does it gain at the middle? As kinetic. What would that graph look like if the total is a constant, and this is what the gravitational potential energy looks like? What would the kinetic energy look like? For those of you that have been in a math class, you might think of a symmetry line. You see that the kinetic energy would look essentially as the mirror image. No matter where I look, the total energy adds to the TME. Now you might see how waveforms are starting to come out of this. And so when we start to have something oscillating, you can start to see how it sort of oscillates like the beginning of a wave. Okay? How many people had a graph that looks something like that to begin with? Yeah, a few people. Yep. So, but you got it fixed. Okay. Now, some other things. Most of this is going to be review for you. Some terms that you need to know. So this is vocabulary. Maximum displacement from equilibrium is called the amplitude. So when I talk about the amplitude of vibration, it's a maximum displacement from equilibrium. We measure that in meters. So it's a length measurement. So the SI unit would be the meter. Now how long it takes to complete a cycle is what we would call the period. So a full cycle is completed in what's called a period. So we'd measure that. We'd say, how long does it take to complete a cycle? You turn and tell that person that you're sitting next to, what is the period of the minute hand on a clock? Tell that person that you're sitting next to, what's the period for the minute hand? On a working clock, none of our clocks are working, but on a working clock, what is the period for the minute hand? Thank you, Riley. 12. For the hour hand, it'd be 12 hours. But for the minute hand, you guys agree it takes 60 minutes for it to complete a cycle? Okay, so the period for the minute hand would be an hour. What's the period for Earth's rotation on its axis? Earth's rotation on its axis. You guys agree that period is 24 hours? How about the revolution around the sun? That's 365 days. Okay? So the idea behind that is period is how long it takes to complete a cycle. Now the SI unit is the second. And then finally, the frequency is what we call the number of cycles completed per unit time. So frequency, again, is a count of cycles per time. The SI unit for that is the hertz. That means it's 1 cycle per second. These two are reciprocals of each other. What that means is that all you'd have to do is take the reciprocal of one to find the other. So this sounds like an equation that we could write down. Reciprocals just are an inverse operation. We'd say that the period is 1 over the frequency, and the frequency is 1 over the period. Raise your hand, you have a calculator with you? Few people? All right. So tuning forks are very common. Very common things to demonstrate sound waves. So see if you guys can hear this. Close your eyes. Close your eyes. Connor, way in the back, are you able to hear that? Okay. This thing is cycling at 256 cycles per second. So it's a 256 hertz sound wave. You guys can hear that? I would like to know how long it takes for it to go through 1 cycle. So it's 256 cycles per second. So the thing's vibrating back and forth 256 times per second. Those that have a calculator. Thank you, Noah. I want to know the period, which is how long it takes to complete one of those cycles. So if it goes 256 hertz, and that's what I can hear, how long does it take to complete one of those cycles? Are you doing that for me, Noah? Okay, so frequency equal to 256 hertz. If I want to find the period, that would be 1 over 256. What is that value?
0.0039.
Confirming? Okay, so it's a very short amount of time for it to go through one of those cycles. Okay? When I played your speaker, I had it set for 1,000 hertz. It'd be 0.001 seconds for it to go through a motion. Okay, that's the idea. Now, I'm going to put these things in for you just simply because these are asterisks, so they're not on your exam or quizzes. But some of you might be doing a simple harmonic oscillator that has to do with a mass on a spring. So the period for a mass on a spring would be 2 pi times square root of m over k. And some of you might be doing something related to the pendulum. We'd say that the period for that, 2 pi times the square root of L over G. And again, it really depends on whether or not you're going to be doing a wave-related project that has to do with oscillators. Some of you will be. Those are not required for exams or quizzes or for enrichment stuff. Okay? Okay, I'm almost out of time, and I think that's probably a good stopping point. So what I'm going to do is I'm going to save the wave classification stuff for tomorrow.